This video presents our paper titled Online Non-Collocated Estimation of Payload and Articular Stress for Real-Time Human Ergonomy Assessment. This work is accepted for IEEE Access journal publication. In this paper, we investigate online methods for stochastic whole body inverse dynamics estimation applied to highly articulated human models. We highlight several limitations and propose an extended formulation in order to estimate the payload and the associated articular stress experienced by the subject under the influence of the payload. Here, you can see an experimental scenario where the subject is handling a payload. A 3D visualization of the human model indicates the payload estimation and also the articular stress estimation. Our proposed approach results in an estimated payload value that is close to the ground truth value. More precisely, the key contributions of the paper are systematic description of the stochastic whole body inverse dynamics problem formulation and its limitations for human articular stress estimation under payloads. Then we present an extended formulation of stochastic whole body inverse dynamics through centroidal dynamics constraint in order to achieve non-collocated range estimation during external interactions. Finally, we validate our approach through payload and articular stress estimation during dynamic human movements such as walking. In our previous work, we presented a stochastic whole body inverse dynamics problem for simultaneous estimation of human kinematics and joint torques for the case of a highly articulated floating-based human model. However, under this formulation, we tightly couple the model constraints and the measurements, which has two limitations: inability to accurately estimate interaction range at links without direct force torque measurements, and coupled estimation of external interaction range and the internal articular stress. These limitations are evident with an experimental scenario shown here where the subject is lifting his dominant arm with a 5 kg payload. Inability to accurately estimate interaction range is reflected through inaccurate payload estimation, and coupled estimation of external interaction range and internal articular stress results in inaccurate articular stress estimation. We extended the original stochastic whole body inverse dynamics problem into a stack of tasks two-step approach, where the non-collocated range estimation step considers the centroidal dynamics constraint along with the range measurements, and the updated dynamics estimation problem uses the estimates from the previous step as measurements. This new approach helps us to overcome the previously mentioned limitations, and it allows us to accurately estimate the external interaction range on links that do not have any direct force torque measurements, and decouple the estimation of external interaction range and the internal articular stress. These results present the effect of different measurement covariances for payload estimation using the approach of non-collocated range estimation. A higher measurement covariance value results in a better estimation. These plots represent the accurate estimation of the interaction range at the hands for different measurement covariance values. The range estimates are consistent with the payload handled by the subject. These plots represent the payload estimation for different measurement covariance values. Thanks to the extended stack of tasks approach, the estimation is consistent with the actual payload, and the resulting estimates are within 10% error from the ground truth value. Here we highlight the benchmark joint torque and joint effort values computed for an ideal T-pose configuration of the human model. For the sake of clarity, we consider only upper body joints such as shoulder, elbow, and wrist joints to highlight the articular stress estimation. These plots represent the joint torque validation using stack of tasks approach when the subject is in T-pose without payload. For further validation, we also highlight torques computed through deterministic inverse dynamics. As it is evident, the joint torques are close to the benchmark values and the computed torque values. These plots represent the validation of articular stress estimation from stack of tasks approach when the subject is handling a payload. In addition to the thorough validation presented so far, we tested and validated our approach of stack of tasks stochastic whole body inverse dynamics through two application scenarios where the subject is performing quasi-static and dynamic human movements with a heavy payload. Here, you can see the estimated payload value is close to the ground truth. Articular stress is indicated qualitatively through spears displayed at the joint locations. Green color indicates a low articular stress value, while red color indicates a high articular stress value. Interaction wrench acting on various links of the subject model are indicated qualitatively through the arrows. Yellow colored arrows indicate the wrench measured through direct force torque measurements, while blue colored arrows indicate estimated wrench acting on the subject. Thank you for watching this video.